Okay, thank you, Purvi. And I would like to thank the organizers for inviting me to give a talk here. So I'm going to talk on localization for Schrodinger semigroup corresponding to the Sub-Laplacian on Heisenberg group. So let me just start with a very basic case, that is the Laplacian on Rn. So this is the standard Laplacian on Rn. And the Schrodinger equation corresponding to the Laplacian is defined as follows. So minus I del t u x t equal to minus Laplacian in x u x t for all x in Rn. So u has to satisfy this equation for all time positive. And at time t equal to 0, u is f. So this equation also describes the evolution in quantum mechanics of a wave or a particle. And so now how do we, so the goal is to solve this PD given this initial data, and we would use Fourier analysis to solve this PD. So let me just give some quick definitions about Fourier transform, those who don't know. So if we assume f is say L1 integrable function on Rn, on the whole space Rn, and L2 integrable also, then the Fourier transform of f is like an integral transform. We integrate against these kind of fundamental waves actually. E of minus I x dot psi. Psi is a point in Rn, and x dot psi is the standard inner product in Rn. And there is some normalizing constant. So this is called the Fourier transform of f. And this is an integral transform, and it actually has a lot of information. It encodes a lot of information about f. So one of the fundamental things is that if you know f, how far you can conclude about f hat. If you know f hat, how much can you say about f? So that's a very classical thing in Fourier analysis. So now if we assume that f hat, this function is also L1 integrable, then we can actually construct f from f hat. If we know f hat, almost everywhere actually, because this is in the Lebesgue measure sense, then I can actually define f also at every point. And sorry. Also, we know that this Fourier transform f going to f hat is a unitary operator on L2 of Rn. That's actually very nice because it gives you that the L2 norm of f is equal to the L2 norm of f hat. Okay, now let us try to solve that Schrodinger equation. But before that, let me define another class of functions which is very useful for our analysis. So when f is a smooth function such that I take any number of derivatives and I multiply with any degree polynomial, and I take supremum over x, it's always finite. Of course, the supremum will depend on the degree of the polynomial and the number of derivatives I take, but that's okay. So this means that the function and all its derivative, they decay faster than any polynomial at infinity. So this is kind of a very useful class of functions, and we denote it as, we call it as Schwarz class functions. And then again, what we because we are going to deal with the PD, so we need to know that if I take the derivative of the function, then how does the Fourier transform look like? The derivative of the function in terms of the Fourier transform of the function. So one can just check using the properties by integration by parts. And if you assume that f is this kind of function which has decay along with faster than any polynomial and all its derivatives also do that, then you can prove that if I take the partial derivative in j direction of f, take the Fourier transform, it's like multiplication, multiplying the Fourier transform by minus I xi j, where xi j is the jth coordinate of psi. Psi is a point in Rn. Now again, if I take Fourier transform in x variable in the Schrodinger equation, let me, maybe I'll show you here. Because it's a linear map, so everything, the equation is preserved. If I take the Fourier transform, what do I get? Let me write here. Yes. So this will be for a fixed psi, you see, because of this property, the Laplacian on u will become mod xi square on u hat. U hat is the Fourier transform, and t is fixed anyway. And then for a fixed xi, you see this becomes like an ODE. That is the advantage. That is one of the applications of Fourier analysis. Then U hat at xi comma 0 will be F hat. And you know how to solve this kind of ODE. It's pretty standard. And you know that for each psi in Rn, the solution of the above Cauchy problem is U hat xi comma t is E of I t mod xi squared F hat of psi. And you can check that it satisfies this ODE for a fixed psi. So again, if I assume f is a Shor's class function, then what we can do is I can take the inverse Fourier transform of this quantity, and then I will get back u, which is the original thing we wanted to find. So again, you can check that u satisfies the Schrodinger equation with the initial data. That is at t equal to 0, you have f. U at x comma 0 is f. Okay, now we can also view this, this solution as something more general, viewing it as a multiplier of the Laplacian. So before that, I'll have to define what is a spectrum. How do we can also view Fourier transform as something more than just an integral transform. Let's see. For each psi in Rn, x going to E of x dot xi is an eigenfunction of the Laplacian with eigenvalue minus mod xi squared. So we can treat Fourier inversion formula actually as the spectral resolution of identity for the Laplacian. So then once you know the spectral resolution of identity, that is the spectrum, then you can actually define functional calculus of the Laplacian. Means that you have a bounded measurable function on the spectrum, and then you can define some kind of linear operator. So let me define here. So given any bounded measurable function on 0 to infinity, we define, so this is just a notation, that is m of Laplacian is like function, f at x is equal to, you first take the Fourier transform, multiply with the function at minus mod xi square, because I'm talking about Laplacian and its spectrum is on the negative real line, then take the inverse Fourier transform. And this is motivated from, so those who are not very comfortable with this, you can assume that suppose your matrix, if you have a matrix which is diagonalizable, and you can talk about polynomial of a matrix also, right? Because you can take powers and linear combinations, and then the matrix will be, the corresponding matrix will be the matrix and the diagonal matrix, and the diagonal entries will be the polynomial in that, right? And then what you can do is you can replace that polynomial with a general function also. I mean, you can talk about it. So this is what is happening here. But here we don't have discretely many eigenvalues. Here they are on the, for Laplacian, they are on the negative axis. So you need more analytic tools to deal with this kind of spectrum here. Okay, so now you see, once I define this notation, then in terms of the functional calculus of the Laplacian, we can write the solution of Schrodinger equation as a multiplier of the Laplacian, where what is this function? It is this function, E of I t mod xi square, right? This function. This is a bounded function. And in fact, one can check that this f going to E of minus it Laplacian of f is a C0 semigroup. This means that as a, if I define, so those who know, as a function of t, it is a semigroup. It is t of t plus s of f, because this is only we have defined for t at 0 is identity. And this is also strongly continuous. And in fact, that actually I will mention in my next slide. This goes to f as t goes to 0 plus in L2 of Rn. Okay. So an application of, so how do you prove this? An application of Plancherel theorem and dominated convergence theorem gives that as t goes to 0 plus, this operator will tend to f in L2 of Rn, in this space, in this norm only. So convergence in L2, we know that in measure theory, if you have convergence in the L2 norm, it does not give any information about pointwise convergence at all. And as analysts, we would like even better convergence. But if I assume that f is a Shor's class function, which I had already defined, then by inversion formula and using the properties of Shor's class function and along with DCT theorem, you can prove that this semigroup E of minus IT Laplacian of f at x converges to f of x for every x in Rn for each point. In fact, you can prove better. You can prove that it converges uniformly to f over every compact subset of Rn. It's a really nice situation because I'm assuming, so this indicates that if I assume f to be more smooth, then the solution behaves in a much better way, right? Because it converges to f very nicely. So that's what this would motivate me to define some kind of Sobolev spaces. And so let me define now. Hs of Rn is space of all distributions, actually. Well, I don't want to go into too much into technicalities here. So all the distributions such that if I take the Fourier transform, take mod square, multiply with this kind of growth, well, it is growth when s is positive and it is decay when s is negative. This is finite, okay? And notice that when s equal to 0, this is by Plancherel theorem, this is nothing but L2 of Rn. That is what I have written. And when s is positive, this is some kind of capturing the growth of generalized derivatives of f. Okay, those who know what I'm talking about. Now, there is a very nice result. That is, if I take s to be large enough, so one could ask, if I say generalized derivative, so do they really give you normal derivatives, the classical derivatives? And the answer is yes, if I take s large enough. So if I take s to be bigger than n by 2 plus j, where n is the dimension here, Rn, then Sobolev theorem implies that Hs is embedded in, so Cjb is j times differentiable functions and bounded on Rn. So that's actually nice. Okay, so now coming back to the convergence issues of the Schrodinger equation, solution of the Schrodinger equation, then it's a problem to find the, that maybe I will say in the next slide. So if I assume, suppose my initial data f is in this Sobolev space Hs for s strictly less than 1 by 4, then it was shown by Dahlberg and Koenig that there exists a set of positive measure for some f such that this limb soup of, actually I should have written modulus here, that's a typo, this diverges. Okay, so notice that what we are looking for is this kind of convergence as t goes to 0. We don't know if the limit exists pointwise, but what you showed is that if f is in Hs of Rn, R, n equal to 1 actually, for s less than 1 by 4, you can always find some f where this limb soup, this is equal to infinity on a non-zero measure set. So you cannot expect pointwise convergence for L2 functions, for example. And see, the third, so in some sense, when S is large, you have more regularities. This means that one has to assume for dimension 1, one has to assume S to be bigger than or equal to 1 by 4 to expect some kind of pointwise convergence. Now the question is, what is the optimal S such that if f is in Hs of Rn, then this Schrodinger semigroup converges to f as t goes to 0 plus. Okay, and this is only this S less than 1 by 4 is the condition for n equal to 1 only. Then, in fact, in the same result, in the same paper, Dahl and Koenig also proved that E of minus IT Laplacian F converges to F almost everywhere as t goes to 0 plus if and only if F is in HS of R, S bigger than or equal to 1 by 4. So in one dimension, the situation is completely solved. And in higher dimensions, so this was in 1982, and the second development happened in 85, I think. When n is bigger than or equal to 2, then Scholin and Luis Vega, they proved independently that limit t going to 0 plus E of minus IT F equal to F almost everywhere. When F is in HS, S bigger than 1 by 2. And they also constructed a counter example for S less than 1 by 4 there. So this problem, after 85, it was open for a long time. There were some developments, but it was completely open. And then very recently only, Larry Guth, Jiachun Li, Xiumin Du, Zhang, in 2 papers, they have proved that for n bigger than or equal to 2, the Schrodinger semigroup converges to F almost everywhere when F is in HS of Rn, S bigger than this n by, there is some double bracket, that's the typo, twice n plus 1. And for S, and this result is sharp except the endpoint. That is, we don't know what happens at S equal to this, but for S less than this quantity, Burgan, he proved a counterexample long time ago. So in the Euclidean situation, it's completely solved except for one point. And I mean, given the kind of technicality of this problem, it's not been studied in many other situations. So now I will try to give some, I will try to study this kind of problem in the context of Heisenberg group. And before that, let me introduce, sorry, I have to also introduce localization because I'm going to talk about localization, yeah, which is slightly better than pointwise convergence. So let me first go to what is, because my title of the talk is localization, not pointwise convergence. So now instead of global smoothness on F in Rn, so as we noticed that if F is smooth and if has F and all its derivatives have a lot of decay, then you have very nice convergence. Okay, but what if we just assume that F is smooth only in an open subset? And we also give some integrability condition on these generalized derivatives, that is, F is in some sublove space, some order. What can we say about the convergence of this to F on any compact subset of U? That is where F is smooth. That is why it is called localization. We're just looking at a local part here. Okay. And nice thing is that because of the linearity of this operator and the density argument, because for Schwarz class function, we always know things are very nice. Actually, the above this kind of problem boils down to the following. That is, we can assume F is identically 0 on a, actually, we can take an open subset. And then F is in HS for some S. We would like to study the limit E going to 0 plus E of minus IT Laplacian F on this set where F is identically 0. We would like it to be 0 actually. So what I'm saying is that instead of assuming that F is smooth on an open subset, you can assume F is identically 0 because we can always construct functions, smooth functions on locally and 0 outside. So this is what it is equivalent to. Then suppose if, assuming the third point, that is F is identically 0 on a compact subset, then if E of minus IT Laplacian F goes to 0, say uniformly on K, then we refer to it as localization uniformly. And if it converges almost everywhere, we say it is almost everywhere localization. And this kind of localization phenomenon is also studied for other families of operators. And one such example is like the partial sum of the Fourier series, that is the convergence of the Fourier series, because that's also a very important question in Fourier analysis. Okay, so now well, maybe I should have mentioned that. So I would like to study this kind of problem because on Euclidean spaces, this is almost it's completely solved except for the endpoint, and I would like to study this problem in the context of Heisenberg group. So let me first define what is a Heisenberg group. The Heisenberg group can be identified with CD cross R. Well, R2D cross R. We are not going to use a complex structure anyway, but it's kind of convenient sometimes to write it like this. So a point in the Heisenberg group is denoted by Z comma T, where Z is in CD, that is the Cartesian product of C, D times, and T in R. And okay, maybe I should have mentioned the group operation first. So this is the group operation. This is the 2 points. The group operation is defined like this. So it is motivated again from quantum mechanics, which I'll not go into right now. So Heisenberg group is a simply connected, I'll come to what is unimodular. This is two-step nilpotent Lie group under this group action. This is the symplectic form actually on CD. And what do I mean by unimodular is that there is a measure on H on the Heisenberg group, which is invariant under both left and right translation by the Heisenberg group itself. And this is nothing but the Lebesgue measure on R2D plus 1. But this is not an abelian group. So this is where things may not be as nice as in the Euclidean case. So, now let me, because we want to study the Schrodinger equation, so we need to have some Laplacian on the Heisenberg group, right? So we consider the following. So it is 2D plus 1 dimensional group, the Lie algebra, and then you will get 2D plus 1 number of left invariant vector fields, which form the basis of the tangent space at every point actually, because these are left invariant, so you can just go to any point. And these form a basis of the vector space of left invariant vector fields on HT. And in fact, the Lie algebra of left invariant vector fields is generated by the Lie brackets and finite linear combinations of only xj and yj. This t variable, this del by del t is not needed. Just by taking the Lie brackets of xj and yj, actually they satisfy some kind of relation. Now, so what is the analog of Laplacian? Because to generate the Lie left invariant vector fields, Lie algebra of left invariant vector fields, it's enough to have xj and yj. So we can define the sub-Laplacian. That is why it is not called Laplacian, the full Laplacian, because we are not taking all the basis elements of the left invariant vector fields. We are leaving out T, this capital T. So if you consider sum of squares of xj and multiply with minus, this is known as the sub-Laplacian or the Cohen-Laplacian on the Heisenberg group. This is a left invariant operator. And in harmonic analysis, another very important part is the convolution of two functions. We define this f star g as this. This is the standard. Because of the left invariance of the measure, you can rewrite it like this also. And then this sub-Laplacian is a densely defined positive. It is a hypoelliptic operator. It is not elliptic, which is still not too bad actually. And it has a self-adjoint extension of L2 of HD. HD is the Heisenberg group, and it also commutes with left translations. That is the advantage. And now, as we saw that for looking at the solution of the Schrodinger equation, we needed the spectrum of the Laplacian. So it's very natural now to find what is the spectrum of this sub-Laplacian for the Heisenberg group. And once you know the spectrum, then in terms of the functional calculus, we'll be able to find what is the solution of the Schrodinger equation. That is why it's important to study the spectrum of this sub-Laplacian, which is still quite explicit, not as nice as in the case of Euclidean. The action of L, so how much time do I have? I think I have to.
So let's say around like 5 minutes.
5 minutes,
Yeah.
okay. Right. So let me just quickly tell you about the spectrum of the sub-Laplacian. Yeah, what do we do is we apply the sub-Laplacian on these kind of functions, which are simple in t variable. and just G is say any function. So we'll get another family of operators here, L lambda, which is again not too bad. It's called special Hermite operators, and its spectral decomposition is completely known on R2D. And then when lambda is 0, this is nothing but the Laplacian on R2D. Okay, then we know the spectral decomposition of L lambda. So let me just quickly go through this. So if I define these functions, ek lambda, zt, so these are Legger functions of order d minus 1. These are very classical objects. These are like some kind of polynomial times Gaussian. And then if I take f star ek lambda, you can check that because they are eigenfunctions of the L lambda. And then ek lambda will be an eigenfunction of the sub-Laplacian with eigenvalue as this actually. And by using the left invariance of the sub-Laplacian, if we assume that f is Schwarz class function, this is again for interchanging the order of integration and differentiation. You can prove that f star ek lambda, sub-Laplacian applied on that, is actually equal to this. So this is like a projection onto this eigenspace. But then they are not L2 integrable, right? So one has to just be more careful. So then the Plancherel theorem in this setting would look like something like this. So that is, you first take the Fourier transform of this in the t variable, and then take the L2 norm in R2D, and then you have a Plancherel measure sum over k, and you'll get the L2 norm of that. So this is important. Okay. And the inversion formula, like in the Euclidean case, the inversion formula is slightly more complicated here because of non-commutativity also. So you have these f star ek lambda, and then you have this measure, and then sum over k, and integrate over lambda. Okay, and this is in L2 sense. So once you have the spectral resolution of identity or the spectrum, we can define multipliers of the sub-Laplacian. So we just work with this spectrum. This is spectrum here. And then I can define multipliers of the sub-Laplacian like this. Right. So M is a bounded measurable function. I can define, this is just a notation again. Okay. Then in term, by Plancherel theorem, this is a bounded operator in L2 because M is bounded. And for LP boundedness, we need more regularity conditions on M. And then now let's come to the Schrodinger equation for corresponding to the sub-Laplacian. It will look like this. So here I'm writing x in HD because I didn't want, because t is the time variable here. Again, as we did in the Euclidean case, in terms of the multiplier of L, we can just actually write like this. Then when f is a nice function, you can check that this will solve your Schrodinger equation. And now again, the question is the pointwise convergence. So this is again a C0 semigroup on L2 of HD. Okay, this again, this should have been the other format. And Plancherel theorem and dominated convergence theorem will again give you that this Schrodinger semigroup converges to F in L2. But again, here also we are more interested in the pointwise convergence. And now, without going much into details and the proof, I will just state one result. So here also we need the condition of Sobolev spaces because you need some regularity on the function for Schrodinger, for convergence of the Schrodinger equation. If I assume F is in this kind of Sobolev space, you can define Sobolev spaces for actually positive self-adjoint densely defined operators. This is like in the functional calculus sense. I assume F is identically 0 on an open subset. So I didn't say that how do we study these kind of convergences is actually one of the common ways is to look at this kind of function. To study the supremum over the set where we want to study the almost everywhere convergence. And if I can prove that it is bounded by certain norm, then by density arguments, I will get the convergence. But here I'm assuming f to be 0. So I can actually also put some kind of a growth in t. That is that it goes to 0 actually at least like t power gamma by 2. So this is the conclusion I have for all s bigger than 1. So you need s to be, well, I mean, this kind of, the method I'm using here is kind of more general. So if I'm sure that if I explore more structure of the Heisenberg group, I will get some index depending on the dimension of the Heisenberg group also. And yeah, so if I assume my f is in Sobolev space for s bigger than 1, then I get that E of IT L of f goes to 0 like t power gamma by 2 on the set where f is identically 0 almost everywhere, of course. And this gamma also has some kind of restraint. Of course, I cannot take gamma as large as I want. It depends on the smoothness. The smoother the function is, the larger gamma I could take. These are some references which I mentioned about the classical results. This is the most recent result. These two are most recent results for Schrodinger equation in the Euclidean space. Thanks for your attention.